Okay, yes. This is, I'm trying to tell you guys, I try hard to be maximally tricky, so you should not rely on stuff like that. So you switched from the score you currently have only to both? Is that right? Okay, so don't do what Gabe did. It is the score you have. He was right the first time. So universes A and B are exactly the same, right? In this game, if you're at 10 points, it doesn't matter if it took 2 rolls or 5 rolls. There's nothing about the rules of the game that take into account the number of rolls. You could imagine a different version of the game where you have 10 rolls maximum or something, and then you need to include these. But as written in the game, it's the number of points you have, and whether or not you've gone bust, that determines everything. And the way we encode this in our modeling is we're going to have a state space, and the state space is only going to have your total, and it's not going to include the time. And then you can check that the state space has the Markov property. So this stuff doesn't matter because it's not included in the state, and the state includes everything that we need. Another way to say it is it's like in snakes and ladders, where if you're on square 10 and you want to know where you're going to go to next, it doesn't matter if it took you 2 rolls to get to square 10 or if it took you 5 rolls. This is the big idea we started the course with, is you should not try to add up all the ways to get to 10. What you should think about is if you're on 10, what happens? And then sort of just iteratively figure out what is the number of ways to get to each square from each square. So very similar to the snakes and ladders thing. Sorry if I tricked people into selecting the wrong thing. I try to be tricky but not mean. I don't know. Any questions or comments about that one? In fact, if you're interested in this, you can also watch the number file video. They do a 5 or 10 minute little discussion about whether or not this matters. It's another example is you could imagine a very similar game where instead of the rules of the game as written, at the beginning of the game you say how many times you're going to roll. That would be a different game, and in that one, of course, the number of rolls matters because it's you don't get to see what you're at, right? In this one, we do get to see where the points are at. Okay. All right, that was that one. Let's see what people did. Can I unreveal the answers? Okay. And then the true falses. Okay, so do you get plus 6 points? 12 people said false. So people think you don't get a reward of plus 6. And in this one, people switched to false. And you guys figured it out. So it is false, false. Very good. So I want to reveal the correct answer. Great. So the majority got it in both. I think this is a common misconception about these things. This one in particular, I think, trips people up a lot. Because it feels like when you roll a 6, you're getting plus 6 something, 6 points. So why do we not get a reward of 6? Does anyone have a nice explanation of why this one is false? Yeah.
The reward is letting you down.
That's right. So the reward, we want it to be the dollars at the end. And if you have 6 points, that's not the same as $6. So you should not think of it as getting a reward of 6. And in fact, in this game, I think the easiest way to think about it is the only time you get a reward is at the end of the game. So the sort of the game happens, you don't get any rewards during the game, and just at the end of the game, you get some number of rewards depending on where you are and did you bank. And in our sort of taxonomy of thinking about rewards, this is 100% the terminal rewards. The only rewards are the terminal rewards. So let me actually draw a little picture of how I'm thinking about this. And there are other ways to think about it. So you can do some weird setup where things are different, but I think they're more confusing. And I was should I explain the other ways? I'm no, it's just going to confuse people. So I'm going to explain it my way. And in my way, there are only terminal rewards. And I'm thinking about these are the states. They're how many points you have. And there's a version where you're still playing and when you're done. So for example, this state over here, which is 3 comma still playing. This is you have 3 points, and you have not yet chosen to bank or not. On the other hand, this one down here, this one is 3 comma done. So this is you got to 3 points and you already chose to finish, and now you're sitting there, you've finished the game at 3 points, and you're waiting for the person to come pay you your $3. And I think of the rewards in this game, they only exist on these done states, and these done states are the terminal states. And that is where we're putting all the rewards. So this game has only terminal rewards. Terminal rewards. The terminal rewards, remember, those are the one-time rewards that you get at a terminal state. the example we did before was the drunkard's walk, where if the drunkard gets home, he gets a 1 point 1 time. And that is different than like the reward, the ongoing rewards, like how many squares it takes until you get somewhere, or how many reincarnations. Those were like ongoing rewards. These are terminal rewards. Okay. And the terminal rewards are at state s comma done, you get a reward of s. You get a reward of s. And I think a lot of people, they mix these things up, and they think like, oh, if you're at state 2 and you roll a 6, then you got a reward of 6, and you're now at state 8. But you don't actually get the rewards until you bake them. So like, if you're still playing, like those are like sort of potential points. They're potential rewards, not real rewards. And you can convert the real rewards into, the potential rewards into real rewards by choosing to stop, right? Then you move to the state, and then you collect your reward. And that is like how this thing is set up. Any questions about this idea or the setup so far? Okay, yeah. And like I said before, you can come up with some like weird other way of setting up this game that I think is more confusing than helpful. So I'm not going to say it, but if you have questions about like, oh, couldn't you set up like this? Please ask, and I'll tell you like yes or no and why it's good or bad. Okay, so let's look at the very last one, which is the value function. And this is the one you guys got wrong the first time, but I think people figured it out. Did people actually figure out what's going on here, or did you just like guess one? Does anyone want to? I guess put your hand up if you just guessed and you're like, I had no idea, I just took a guess. Okay, so about half people. Does somebody who knows, can someone explain why this is false? Let's review what is the definition of the value function, right? So the value function, right? The value function v, this is like one of the big important players in this world, the value function. Also thought of as a vector, but it is really a function that inputs states, and if you stack all the states together, you get a vector. It's the value of state s. Remember, it's the total return, or the total rewards, given that you start at state s. So you start at state s, you play the game, you make your choices, and then at the end, you have some amount of total return you've gotten throughout the whole game. And the value function is on average, how much do you get? And the important part is it starts at state s. So what is v of 0? V of 0, it's the expected value of the total return started from the starting state. And I guess I mean 0, comma, done. Let me just say start. Okay, so why is this not equal to 0? Yeah.
Like when you play this game, it's obvious that you're not going to get 0 points on average.
Yeah, you have a non-zero chance of getting some points, and as soon as you have you can't get negative points, right? So this is a random variable. Sometimes it's 0, but sometimes it's not 0. And so what is it on average? It's some positive number. And in fact, this v of the starting state, this is some people call this the fair price of the game. The fair price of the game. So like if I was a casino and I was like, I'm going to let people come in to my casino and actually pay them $1 when they play this game, I want to make sure I charge them at least the fair price of the game. Otherwise, people will be on average taking money from me, right? Like if I set my price too low, then when people play the game, on average, they get this amount of money, right? They start the game at the start, and so on average, how much do I have to pay them? It's this much. And so like that's the sort of fair price where the casino would break even. The casino would make sure to charge a little bit more, and I guess the trick is that people are not good at calculating this, but you guys will be. Okay. Does that make sense for what the value function is? Okay. Let's start with a couple definitions. So this is a little ambiguous here as written. We had the value function before, and it was totally unambiguous because there were no actions to be chosen. As written over here, it's like I said, the expected value of the total return given you at the start. But of course, that depends on the choices you made, right? So what does this mean? Like, what does it actually mean? And so to make it careful, what I'm going to do is I'm going to add a little pi over here, v pi. And so there's going to be pi's. Pi in this course is not the number 3.14. The total return, I'll say under pi. Under pi. Under pi. And pi stands for policy. Pi equals policy. And policy, an equally good word for it would be strategy. Strategy. And what it is a choice of action at each state. Okay. And so if you like predetermine your strategy, you say like, I'm always going to, I guess the example we did was 10 points. You say, if I have less than 10 points, I will always roll again. If I have 10 or more points, I will stop. That is a policy pi. So example, pi is the roll under 10 points policy. And I don't know why they call them policies, but that's what they call them. They don't call them strategies. There's one other thing I gotta do a little amendment. So if you have some policy pi, you can calculate what this is. The fair price of the game, usually people say, is for the optimum policy. So V of, and people use this terminology, pi star. Start. So the fair price of the game is like the best player who makes the best possible choices, what would they get on average? That's the optimal policy, so pi star is the optimal policy. Pi star is the optimal policy. And what does optimal means? It means it maximizes the value function. So v pi star of s is greater than or equal to, actually, why don't I just say maximum? Let's do maximum. Is equal to the maximum over all possible policies pi of v pi of s. So if you play with the best possible strategy, then you get the most value out of everything. Yeah, question?
Is it possible for a game to have no optimal policy?
That's in the ones we're doing, they always do. I think as long as you're like avoiding like infinities and stuff, like as long as everything is finite, then it will. Yeah, that's a good point. You can make some. Oh, okay. You know what? That's not true. You can have some sort of like real analysis situation where like the policies are like all the numbers between 0 and 1, not including 1, and it's better to be close to 1. But everything will be discrete and like everything will have an optimal. And you should think of there is an optimal. Yeah.
Is there only one optimal policy?
That's also a fantabulous question. No, there might be more than one. That's true. Sometimes it's like neutral. It's like you're in a situation, you can do this or this, and they're both fine. Yeah, that's a good point. Great. Okay. Where was I going to say? Oh, yeah. Okay. This is the important observation that I want to make that I haven't said out loud yet that I think is really good. You might remember the first 4 weeks of the course before I introduced any decisions, right? We were just doing Markov chains, and then we did Markov chains with rewards. Why did I warm up with that? Well, once somebody tells you what the policy pi is, all the stuff we did before is 100% of the game, right? So once pi is fixed, Markov decision process, that's what we're doing now with choices and actions, becomes Markov reward process. Right? So a Markov decision process, this is what we're doing in the course starting now. So this is like week greater than or equal to 4. And then a Markov reward process was what everything we did before, week less than or equal to 4. So like, like finding how many reincarnations you have, right? Once you've chosen the actions you're going to take, then there's no actions left, right? And like another way to say it is a Markov decision process is this like triple, right? It's the the state, then the action, and then the reward, and then the state, the action, the reward repeated. State, action, reward. dot, dot, dot. So that's like a Markov decision process. You see the state, you get to choose the action. But if you've fixed a policy pi, then you've already chosen the action, and people will write it like this, pi of s, right? So the action that you chose is a function of the policy. The policy tells you exactly what you're supposed to do. And then if you follow the policy, then it's just a Markov reward process. And we know how to do stuff with them already. So we can calculate things. What we don't yet know how to do is find the optimal policy. That's what we need to learn how to do. But we will get there. Okay, so that's policies. And a good example is the roll below 10 policy. And very technically it's a function. So I guess the roll below 10 policy, let's go back up to it and write it down as a function. The roll under 10 policy is pi of s. Pi of s equals roll if s is less than 10, and it's bank if s is greater than or equal to 10, right? It's like an honest to goodness function that inputs the state and tells you what do you have to do. Okay, so that's the first piece of terminology, a policy and this value function v pi, right? We know what value functions are from our Markov reward processes. Now they depend on the policy pi, but if you fix the policy pi, it's the same thing as before, and we can do all sorts of stuff. Questions or comments about any of that? So policies are going to be an important part of the course. All right. Let me introduce one other piece of terminology. So we have the value function v. There's another type of value function called a Q function, and Q stands for quality, I believe. So this is yet another value function. So far we have v pi, and now we're going to introduce this Q one, and it depends on pi. So let me try again with that Q. Q sub pi, and the value function depends only on the state, but the Q function depends on the state and action. So it's an S comma A. SA. It depends on the state and action. And okay, let me rewrite the value function so that we can compare and contrast them. The value function is the expected value of the total return under pi. So you follow pi forever and you start at state S. So you're at state S, you do whatever pi tells you, you end up at some other state, you do whatever pi tells you, you end up at some other state, you do whatever pi tells you, and then at the end you add up everything you got. That's the value function. What is the Q function? It's exactly the same thing, except there's one exception, which is you do the action A first, and then you follow pi after. So it's the expected value of the total return of doing action A0 equals A and pi after, given you start at S. So you start at S, you do the action lowercase a that you were told in the function, and then after that you follow pi forever. And so this is like a way of being like a little bit rebellious. You don't want to follow pi forever. You're like, haha, I'm going to do one step of not pi and then follow pi. This is called the Q function, and of course they are related, and this is actually why the Q function is really useful, is it tells you things about the value function. I'll give you the first little hint. What is Q pi of S, pi of A? Does anyone know, or pi of S, rather? Does anyone want to tell me what that would be equal to? You want to take a guess?
Would this be the value function?
Yeah, that's right. This is just v pi of S. So this says, I'm going to be so rebellious, and instead of doing the action you told me, I'm going to do pi of S. Wait, but that's what you would have done anyway. So these are the same. You're doing the same action. Okay. So this is an example. Okay. Why do we need this Q function? You're going to see in a second. And the example I'm going to give you guys is, let's try to figure out what is the optimal strategy in PIG amongst the roll below K strategies. So we talked about the roll below 10 strategy, but you can make up a roll below K strategy for every K. So this is like a whole sequence of policies. There's pi 1, roll if you're below 1, otherwise stop. There's pi 10, we talked about, roll below 10 if you stop. There's pi 100, right? So you choose a fixed value of K, and we're always going to roll again if we're below K. How do we figure out the best value of K? So of these policies, we want to calculate how good the policy is, and we want to report back what's the best value of k. And I want you to think about it for a little bit and see if you can like puzzle out like what kind of calculation would you have to do to figure it out. This is what they do in the number file video. So if you've already seen it and you know the answer, don't just put it in -1 so I know that you've seen it already. And my hint is to do 2 calculations and set them equal. So calculate the value if you stop and calculate the value if you choose to roll again. Those are Q functions, right? So I'm saying if you chose to stop, that would be like Q using the stop action or Q using the roll again action. What would happen? And how should these 2 numbers be related to each other? So I'll let you guys think for a bit. I want you to puzzle with it. If I just tell you the like formula, I think it'll be less memorable than if you try to work it out in the pig game. So where should you stop to make the optimal policy? And the hint is calculate these 2 things. So you're at K. If you choose to stop, what happens? If you choose to roll again, what happens? And how should these be related? Okay, I'll give you a couple minutes to think. If you have a question or comment, you can also let me know. I guess you could quickly go watch the number file video and then put in -1. Okay, so if you haven't figured it out yet, don't rush to put in your answer. I'll give you guys some more time while I write some stuff when the time's up. Okay, so don't feel rushed. I'll leave this open for now, and then I'll give you some hints. Actually, I'll do half the problem for you, okay? I'll calculate the value if you stop. All right, here we go. So what we're calculating is if we let pi k is the stop below k policy. What we're calculating is q pi k. So the q function when you choose to stop and when you choose to continue. That's like the notation you would use. Roll again. You could also describe it in words, which is if you choose to do this thing and you stop, what happens if you choose to do this thing and you roll again, what happens? And one of them, and I'm doing it at x equals k. So let's put k as the state. So starting at this like critical K point. One of them is very easy. I guess I said I would do it for you, but now I feel like I want to make you do it. Does someone want to tell me what if you choose to stop, what happens? Yeah. You get K. Yeah. So you're at K. You chose to stop. So it's an average of what will happen to you, but what will happen to you is 100% of the time you will get K points. So this one is K. This one is K. That one's exactly K. This one's a little trickier. Did anybody happen to work out what this one is? So this is you're at K. You're following the policy that if you are you stop below K afterwards. So you're going to roll and then follow the policy forever after that. Did anybody figure out what this one is? Yeah.
20.
You got 20? Did anybody get anything else? It's related to 20, but it's not 20. Yeah.
I did everything. I got 20 minus K all over 6.
20 minus K?
Yeah. Oh, minus K all over 6 plus K.
Oh, plus K. Like this?
Yeah.
Yes. I think that is equivalent to what it is. Let's remember what the definition is. I think this is correct, but its algebra is slightly different than mine, so we'll have to see when I get the right answer. So, question? Okay, so what is the definition? The definition is it's the expected value of our total return starting from where we are and doing what it says. So we start at K, S0 equals K. We're going to roll again one time because that's what it told us to do. And then after that, we're going to follow the policy. So then pi k. That's the definition. So it's the value function, roll again once, and then follow pi k. We're at k right now. So when we roll again, what's going to happen is one of 6 things will happen. We'll either be busted. And that happens with probability 1/6. If we roll a 1, if we roll a 2, then we will be at state k plus 2 with probability 1/6. And I guess to be even more specific, we'll be at k plus 2 and still alive, right? Whereas like if we roll a 1, we get 0 points and we're busted. Or we can be at k plus 3 and alive, or we can go all the way to k plus 6 and alive. So this is technically what I've written here. This is the distribution of S1, right? S1 is a random variable. We started at position K. Where are we after we do the thing? We're at position S1, and we're at all of these states. And now, to figure out our total return, we have to say, what are we going to do? So we're at K plus 2. Are we going to roll again, or are we going to stop? Which one are we going to do? In general, you have to, it depends. Like maybe you do a lot of crazy stuff. But in this particular case, it told us, follow the policy pi k. And pi k says, if you're above k, you stop. So in all of these situations, k plus 2 to k plus 3, k plus 6, we're definitely going to choose to stop. And therefore, what's going to happen is in all of these situations, we will bank our points. And so we will either get k plus 2, k plus 3, or k plus 6 points. So what is it on average? It's the average of all these things. So policy pi k says stop at all these. Says to stop here. Okay. And so what do we get is we get the average of all of these things. So 1/6 of the time we get 0 points as our return. The other 6 of the time we get k plus 2 points plus k plus 2 times 1/6. Then sometimes we get k plus 3 1/6 of the time, all the way up to k plus 6 1/6 of the time. And the way I would write this is we have 5 copies of k, all with a coefficient of 1/6. So this average is this. I guess this shouldn't be an equal sign. This should be a notice. This equals this, and then the equal sign is this expected value equals that thing by the notice. Okay, so what is the answer? Following along some more. That's equal to k times 5 over 6 plus, and then you have 2 plus 3 plus 4 plus 5 plus 6. 1/6 times 2 plus 3 plus 4 plus 5 plus 6, which happens to be 20. 5/6 k equals 20 over 6. Okay. So there you go. Those are the 2 calculations, and they are technically calculations for the Q function. And it says if you're following the strategy, you choose to stop, then you're going to get k points right away. If you choose to roll again, you're going to get 5 over 6k plus 20 over 6 points. And now the question is, what is the relationship between these two things? So for some values of k, they are related one way. For other values of k, they are the other way. So I think this is the way I think about it, is I say, if k is too small, i.e. k star is bigger than k. So this is the situation where you're being too conservative. Like imagine k equals 1. You're like, I'm going to roll again only if I have less than 1 point. Otherwise, I will stop. I have 2 points, stop. Like, what will happen in that situation? Which one will be bigger? So q pi k of k stop versus, so this is like an inequality. Which one is bigger? Okay, roll again. So if you are being too conservative, then which one is bigger?
K star.
K star is bigger, but under the policy pi k. So this is like you're following the policy pi k and you choose to stop, and this is like you're following. Remember, this is our like rebellion, right? So the policy pi k is like too conservative, and we are doing rebellion against the policy, and we're like, haha, policy, we're not going to listen to you. We're going to either stop or roll again. Okay, and the policy is too conservative. So which one will be bigger? Yeah. Yeah, rolling again. So this is like the policy is too conservative, and we're like, policy, you're being so stupid. Let's be more aggressive and greedy. We can roll again. So we'll get more points by rolling again in this situation. What happens if k is too big? K is too big. Too big. This is like too greedy. So k is less than k star. I guess I should always write them the same way. So which one will be bigger? K stop and q pi k of k roll again. Well, in this situation, it's the reverse, right? It's like the policy is too greedy, so we shouldn't listen to the policy. We should stop, right? At the k point, k is so large that the policy is trying to be all greedy, but we should have stopped. We should stop. So this one is better. And this is how I think about this problem in terms of greedy and not greedy. Okay, so that happens if it's too small. That's what happens if it's too big. What happens if it's just right? For k star. K star of k star, comma, stop versus q pi k star of k star, comma, roll again. Well, at this situation, at the very optimal one, you should be like neutral between them, right? K star is so perfectly tuned that if you roll again or if you choose to stop at that point, it should be like the same thing, right? And that's because k star is the perfect thing where it's not too small and not too big, right? If it's too big, you're being too greedy. If it's too small, you're being too conservative. And if it's just right, then these are exactly equal. And we have formulas for these now. If you choose to stop, that's k star. If you choose to keep going, that's 5/6 k star plus 20 over 6. Okay? And if you rearrange, you have this equation, you solve it, you move it to the other side, it says 1/6 k star equals 20 over 6, and so k star equals 20. All right. I'm curious how many people got that answer in. I guess if you're putting an answer in now, don't put in 20. Put in, if you didn't know, then put in -2 for the flag. I'll let people put their answers in here while I take a sip of water. Any questions or comments about this derivation? We just found, of the policies pi k, we found the best pi k star, but we did have to use some sort of like logical intuition to figure it out. Okay, let's take a look. Oh, that's the wrong one. Oh no. Okay. All right. Okay. Yeah. How many people actually figured out it was 20? 6 people figured out it was 20, and nobody watched the number file video. Okay, that's very good. Great. Okay. I do think 21 is also correct. If you said 21, I think it's equal. There's a bit, and it has to do with the fact that you never roll a 1. I don't remember exactly how it works, but there's something like that. Okay, are there any questions or comments about this thing? Okay, yeah.
So it's not because I did get it a different way. The way
Okay, how did you do it?
What I did was I figured out that 3 minus k over 6 is the average you would get after one roll, so I decided that to k. So like, okay, we're gonna get k.
Yes, okay. So I think yeah, this is sort of equivalent to my random variable over here. I was like, it's either k plus 2 or k plus 3 or k plus 4, k plus 5, or k plus 6. You could have said it's k plus something, right?
Yeah.
So you kind of like did a factoring earlier on. Yeah, that's great. Okay, so this way is nice. There's a couple lingering questions. So open questions. So we've sort of figured out the best of the roll below policies is that k equals 20. Here's a question: is pi star equal to pi 20? And we said pi star is the best possible policy. We said pi 20 is the best policy of the roll below k policies. But could there be some like other super secret policy that isn't a roll below k policy? Like, I don't know, at 107, you start rolling again, right? So the number of policies is much larger than the number of roll below k policies. So like it could be that there's a super secret policy out there that isn't this one. So that's interesting. Like we sort of maximized in this like restricted class. And like more generally, how do you find pi star in general? Pi star in general. Okay, that's one question. The other question, which is, what is v pi star, or let's say pi 20? So you follow the roll below 20 policy. What is the value function? So this calculation told you, okay, if you're at 20, that's like the borderline between rolling again or not. But it doesn't actually tell you, like on average, when you start at 0 and you follow the policy, how many points you get, right? This is the sort of the fair price of the policy, i.e., what is the expected value of your total returns? Total returns started at 0. As 0 equals 0. Okay, and the second question they talked about in the number file video. So let me play what they were doing.
Because there's a much easier way, just run a million simulations.
Well, okay, so what's going on here? So I guess let me show the theoretical. So he calculates these theoretical dots. The blue dots are from simulation. So this is a Monte Carlo simulation. Anytime you have something in probability class or anywhere else, I guess, where the answer is an expected value, you can always approximate it by like, I'm just going to simulate it a million times and take the empirical average. That's what people call it. So you can always approximate the value function by doing empirical averages. And then he also calculated the true average, right? And so this is like the difference of what's the average of a million dice rolls and what's the true average of a dice is 3.5. And he calculated these green dots. And he also said it's ridiculously complicated. It took him over a weekend because you have to add up the statements. What he said is not true. And your homework problem is going to be to do this graph. But it's going to run in like less than a second. Okay, so and the reason, and you actually could have already done it. It's an extension of what we did on the first assignment, and that is because of what we said before, that if you fix a policy, right? If somebody says I'm doing this policy, like the stop below k policy, where's my observation? Once you fix a policy, it just becomes stuff from weeks less than 4. So if somebody says I'm doing the roll under 20 policy, you can how do you calculate the value function? You use the baby Bellman equation. So recall, we had the equation, the v pi's satisfy the baby Bellman equation. Okay. So can solve. Or you can do it with the Markov chain and the infinite sum, the matrix, lots of different ways. Yeah.
Yeah, I was gonna sort of comment that if we use like value iteration, aren't we effectively
Yeah.
doing the same thing as a Monte Carlo simulation?
No, that's not true. Yeah, so value iteration is equivalent to doing some partial sum of the matrix powers m, right? So what you are doing is when you do value iteration, you're doing some, there's some answer which is the infinite sum, and value iteration, if you do it with 1,000 iterations, you're doing the first 1,000 terms of that. So you're approximating the true answer by taking something that is truly an infinite sum and approximating by a finite sum. When you do a Monte Carlo simulation, what you are doing is in the matrix M, there's true probabilities. Like what's the probability to go from square 6 to square 7? Or the probability to go from 6 to square 8? And we know those probabilities, like we know it's a sixth. When you do a Monte Carlo simulation, you're approximating the entries in the matrix with like samples of them. So instead of saying the probability is 1/6, you're like, in how many simulations did we move from square 6 to square 8? So they're actually very different. And so it's true the value iteration is like approximate in a certain sense, but it's a very different sense than the Monte Carlo. And this thing that he said, right? He's like, oh, you have to run it over the weekend because you have to add up all the different ways. That is exactly what we started the class with, right? We're like, if you want to figure out snakes and ladders and like how many ways are there to get to square 10, you should not start counting up all the different ways that the dice can add up to 10. You got to do it sequentially. How many ways after 1? How many ways after 2? Actually, I like interview places really like these types of questions because if you don't know it, you just like get screwed, right? So like this is like a common question on like Google interviews is like how many ways can a knight move from this square to that square? If you start adding up all the different ways, it's going to take you forever. You have to do it with this like Markov chain method. And similarly, you guys will be doing it on the second homework, which I think should be posted tomorrow. So okay, that's the vpi. So you're gonna recreate this graph. And I want it to run in less than 1 second, so not over the weekend. Okay, that's one thing. Two. Okay, great. Okay, so we're gonna do that. How much time do I have left? I have a little bit of time. Okay, any questions or comments?
I did have a general question.
Yes.
About the policy.
Yeah.
So is it the case that the gut strategy isn't a function of the state, like some sort of random?
That is a fantastic question. In some situations, that can be a true thing.
Does it ever come up in practice at all?
In practice, it doesn't typically come up. But what does come up is even though the optimal strategy is not a random strategy, it turns out that you often need to use random strategies to explore. So even though the optimal strategy is not a random strategy, while we're on our way to finding the optimal strategy, we will use lots of random strategies, and that will help us make sure we don't miss the optimal strategy. So we'll see that. That'll be a big theme in the course later. That's a fantastic question. So yeah, I wrote it over here as pi of s, and technically pi of s should be a random variable. So here I wrote pi of s. Where did I wrote pi of s somewhere? Oh yeah, okay, here it is. I just said pi of s is roll if s is less than 10, or bank if s is greater than 10. Pi of s equally well could have said roll with probability 90% if this happens. The key thing is the distribution should depend only on s. So if you know the state s, you know like what you're going to do. And maybe that involves flipping a coin or something, but like you gotta know what to do. Yeah, fantastic question. Okay. So the next thing that we're going to do is we're going to learn how can we're gonna solve. So this one we actually already know how to do. Second question we already know how to do. This question is still a great question, and we're gonna learn how to do this. And the answer to do this is we're going to use the Bellman equation. And you might say, wait, didn't we already do the Bellman equation? Well, the Bellman equation we did was the baby Bellman equation, and that's when there are no actions. And I'm gonna start to show you the real Bellman equation right now. Actually, maybe I can fully do the real Bellman equation. So the real Bellman equation, it's for a decision process where there are actions, and it's an equation that doesn't just tell you v pi for some fixed policy pi, it finds pi star for v pi star. And the way I'm going to write it is I'm going to relate v pi star and q pi star. And v pi star and q pi star are related, and you can plug them into each other to get just one equation. But how am I going to do it? So this is an equation that the optimal policy satisfies. So not just any policy, but the best one. Okay, and this is super useful, right? Because it's like even if you don't know what the policy is, you write down the equation, you try to solve the equation, and just like before, that will help you learn the policy. Okay, and so here's the thing. There's two relationships we need. Let me open up my notes so I don't get this wrong. Okay, yeah. So here's the first thing. They're both very like kind of simple ideas, and if you write them down carefully, you'll get it. So v pi star of s. The first thing says v pi star of s is related to q pi star of s comma a. And there's some relationship over here, and you have to do some kind of maximum. And the question is, what kind of maximum? So a is in what? What is the maximizing you do? So v pi star of s says we're going to follow the policy pi star forever. And how much value do we get on average? And q pi star says, okay, we are going to follow the policy pi star forever, but first we're going to do the one sneaky a. All right? And if pi star is really the optimal policy, these two things have to be related. And in fact, it's a very simple maximum. It's a maximum over all the possible actions. So it's a maximum over all the possible actions that are available at state S. And in words, this is just saying to be optimal, you gotta do two things. First, you gotta do the optimal action A now, and then do the optimal actions forever after that, right? So this is like a really simple idea. To be optimal, must do, you got to do two things to be optimal. Two things. Very, very simple. Number one, do the optimal thing now. That's the A. So the optimal thing now is this A. So first you got to do the optimal thing now. Right? And we know it's the optimal thing. We're looking at all the possible A's we could do. We're taking the best one. That's going to be the optimal thing now. Then, very simple, after that, follow the optimal strategy after that. Okay, and you might think this is a very silly equation. So we're going to follow the optimal strategy after that. It's baked in. So this is saying if you knew q pi star, you could figure out v pi star. Right? If you could figure out how to follow the policy pi star forever, and then just like look at one step, then of course v pi star is the maximum of that. So it seems like we haven't done anything. But the real trick is that you can do it the other way too. So q pi star is actually going to be related to v as well. So this is, I guess this is the reverse. Let me do it in a different color. Q pi star of SA is also something in terms of v. And so we're going to have v star in terms of q star. We're going to have q star in terms of v star. You got two equations. If you plug one into the other, we're going to be able to get one nice equation. And so how does this one go? So what is q pi star of SA? Remember, the definition is it's you do action A now. So A0 equals A. And you start at state S. Let me write it like this. So we're going to do action A now. We're starting at state S, and we want the total return. And I'm going to go back to this notation of the G's. Let me write it. I'll write it as rewards. Okay, R0 plus gamma R1 plus gamma squared R2 plus dot, dot, dot. So it's the sum of the rewards. That's the total return. All right. And I'm going to break this apart as two things, which is you got the reward now. So it's the reward you get now, given S0 equals S and A0 equals A, plus there's all the rewards you get later in the future. And those can be written as R1 plus gamma squared gamma times R2, and so on. And that's also given S0 equals S and A0 equals A. And you follow policy pi forever. So S, I guess, let's say pi star after. Pi star after. It's pi star after. All right. So far, this should remind you sort of the derivation of the baby Bellman equation, right? Where the whole point is that the rewards split into two parts. There's the reward you get now, that's R0, plus all the rewards you get in the future. All right. The reward you get immediately, that is some kind of reward. It depends on the action you take, but we know the action we take, we know the state. This is some kind of reward vector. And so this is like the R vector. This is the reward vector. And now it depends on R, S, and A. So this is like R, you should think of it as RSA. R of SA. The reward on average that you get if you're at state S and you take action A. All right, so that's a nice equation. This one over here, this says we're going to start at state S, we're going to take action A, and then we're going to get all the rewards after that. And we're following pi star after that. So this really is really closely related to the value function, right? The only difference is this would be perfectly the value function if only I knew where we were at time 1, right? Because the rewards start at time 1. So this is almost like the value function, except I'm starting at the wrong time. So as usual, it's a Markov chain. If you know where you are at time 0, and you want to know where you are at time 1, you just condition and sum. So this second part is equal to the expected value. I think this thing before was called G, but let me write it out again. R1 plus gamma R2 plus dot, dot, dot. And I'm going to condition on one extra thing, which is what is the value of S1. So S1 equals S prime. And then you have the probability to go from S to S prime. So it's the probability that S1 equals S prime, given S0 equals S, and A0 equals A. And you sum over all possible S prime. Okay, so the expected value, you can condition on all the possible things for S1, like where are you going to be? And then you have this expected value over here. But this thing is precisely the value function again. So this is equal to this. This is a kind of a probability matrix, but it depends on A. So I'm going to write this whole thing. This is equal to, I'm going to write it like this. I'm going to write M, and then I'll put A in a superscript. MA times V pi. V pi. And it's V pi star. So why is it MA times V pi star? This is the matrix M. It depends on the action A. So depending on what action you chose, you'll move to different states. And this is the V pi star, which is the optimal value function as a vector. And if you flow it forward in time by M, then you get that expected value. So overall, what is this saying? It's, as an equation, it's saying Q of Q pi star of S comma A, it's equal to the reward vector, depending on the state and the action, plus you move forward in time by applying this matrix that depends on the action you chose, and then you evaluate that at S. And this is extremely similar to the sort of the baby Bellman equation we had before. So before we had the equation, the baby version was V equals R plus MV with a gamma. I guess there's a gamma. That was the baby version. And the grown-up version is basically the same thing, but now it depends on actions. So the value function becomes the Q function. It depends on the actions. The rewards also depend on the action that you choose A. And last but not least, the matrix that moves you forward now depends on the action. So if you choose a different action, you will have different distribution of things that happen to you. So there's sort of a different M's that can happen to you. So far, this is all pretty abstract. We're going to go back and do this for the pig game. So let's write down what the two matrices are in pig, or the rewards in pig. So maybe I'll do that as a picture. So and then I'll show you how these two equations relate and how you solve them in pig. So in pig, we were thinking of the states like this. with alive and dead, or busted or not busted. So this is alive, and this is done. So these were the states. And if you choose to stop rolling, then you always move to the done state. So if you choose to stop rolling, let's say stop rolling is like this. So you will move down with a 100% probability if you choose to stop rolling. If you choose to keep rolling, then you kind of move forward like this. So this is keep rolling. And you have a 1/6 chance to go to 0. So there's sort of two matrices that are in play. If you stop rolling, then you definitely move down here, a 100% chance. So that's going to be a very simple matrix. If you keep rolling, then you're going to have a matrix that has a 1/6, 1/6, 1/6 to move to all these states, but also a 1/6 chance to move to the done state. And those are the two matrices, M, A. So one is, you're going to have M stop rolling and M keep rolling. And together, that will give you a nice equation. And then we're going to solve that equation on the computer with value iteration. That'll be all next class. But okay, very roughly speaking, this is how we're going to solve things in this course. It's all about chasing down this Bellman equation, which we're going to go into in more detail next time.